So our objective is to understand the relationship between heat and work. And so, as we always do, we very carefully write down the first law that says the change in internal energy of a system is equal to the heat plus the work either entering or leaving that system. We also have deduced the fact that the change in internal energy, delta U, is equal to the heat produced from a chemical reaction at constant volume, and that delta H, the change in enthalpy in a chemical reaction, is the heat released at constant pressure. We also know that we can measure heat entering a system if we know the heat capacity C and the change in temperature. But we also have another extremely important relationship for U, and that is that the thermal energy of a system is equal to the average energy per molecule times the total number of molecules. And we can write this then as the total number of molecules times 3/2 Boltzmann constant times the temperature. That remarkably simple expression. And we can see immediately why heat added is directly proportional to delta T, because the average energy of a molecule increases directly proportionally with that temperature. So we want to keep that expression for U thermal in mind, because it turns out to be very important when we're analyzing heat and work in a system. All right, so the next thing we want to do is to calculate this relationship between heat and work for a system that can actually do work. And that brings up this issue of the machine that is actually involved in the execution of the conversion of heat to work. And it again reminds us of Lord Kelvin's very famous statement that I can never satisfy myself until I can make a mechanical model of a thing. And so we're going to see that when we analyze heat and work in thermodynamics, the first thing we do is to construct a machine. And we're going to construct a machine that's capable of clearly demonstrating to us physically what happens when we exchange heat and work with the system. The next thing we're going to involve is the perfect gas law. And the perfect gas law, as we know from the previous chapter, is PV equals nRT. The pressure times the volume is equal to the number of moles times the gas constant times the temperature. And we say, why are we introducing the perfect gas law when we've got a machine? We've got to worry about all these mechanical parts and so on. Well, the genius of analyzing the conversion of heat to work comes down to the fact that although we have a machine, in this case we are creating a machine out of a cylinder, out of a piston that contains gas, compressible gas, we're establishing the downward pressure by adding the atmospheric pressure and whatever weight we want to put on it that adds to that pressure. But it's what happens inside that machine that really matters for the conversion of heat to work. And then finally, we want to keep extremely careful track of the first law of thermodynamics, which the change in internal energy of the system is equal to the final internal energy minus the initial internal energy. And finally, this important relationship between pressure and volume is represented by the trajectory of a particular act on a plot of pressure versus volume. So let's look at this in more detail with higher resolution.